theory and then do like hypothesis testing. So you could teach entire courses on each one. So you're going to try to like squeeze as much as possible. So the setting is, we encountered this when we talked about the Rao-Blackwell theory. Sorry, not Rao-Blackwell, the Kramer-Rao bound. And we try to sort of see what Fisher information means. And so we recall I introduced this idea that so decision theory is very general, but we look at the case where we have IID samples from like a base density or a base family of distribution. So you can think of this as defining a model based on a single sample, and then we have a model based on the sequence IID drawn from this. So really the statistical model is the distribution or the family of parameters describing, or say parametric family of distribution describing the joint distribution of this guy. So this is going to be the setting that we're going to talk about for like the next, let's say, 3 lectures or so. This is the setting of asymptotic theory. And the idea is, so I mean, suppose I have this IID sampling and the true parameter that's generating. So I have a parametric family, and the true parameter that generates this sequence is some theta star. Okay, and then you have a procedure to estimate this parameter, and you view this as a decision rule. It takes like the entire sample of size n, and it produces an estimate like theta hat. So this decision rule, generally speaking, depends on like the exact problem that you set up, but usually it's sufficiently general that you can say, I have a decision rule for any sample size of size n. So if you give me like one more sample, I'm not going to go like run into issues. I have my procedure sort of is extendable in an easy fashion. So for example, you have the Bernoulli case, trying to predict the probability of a coin flip. You use the sample mean. Sample mean easily generalizes to any number of samples. So you really have a family of decision rules, like a procedure or like prescription to define estimators for any number of samples. Okay, so we're in that setting. And so I want you to like keep this setting in mind. And let's now, with this setting, go back and see if I have the same setting here. So, okay, so that's the setting that you're looking at. We have, let's say, the base probability model. We have a sample size n. And then we have, we want to define a procedure that, so the full model is like the family of product measures if you want. But I want to define a procedure that gives me an estimate of the true parameter. And one general family of such decision rules or procedures are these M-estimators. So an M-estimator is an estimate, or let's say an estimator, that is obtained by an optimization procedure. Okay, so you define some sort of a function, m theta, or like a family of functions that operate on your sample. In this case, operates on a single sample. And then what you do is you form these empirical averages based on the entire population, or based on the entire sample, and then you maximize. So you maximize this function. This gives you an estimator. Okay, so this defines a general class of estimators that easily extend to any number of samples that they have. I just have to pick this function, and once I have it, I can form these empirical averages. They're easy to calculate, and if the function is easy to calculate, and then I have to solve an optimization problem. So a very special case of this is the MLE. Okay, so MLE is an example of this. So anyone can see the connection between the MLE and this M-estimation procedure.
This is like the function as the M function.
Close. but not exactly the likelihood. The log likelihood, yes, yeah. So great. So if you have, remember the joint density is like the product, I from 1 to n p theta of 1 of xi. So the log of this as a function of theta is the log likelihood, right? And I can also normalize it by 1 over n. That doesn't change the maximizer or the likelihood. Remember, the likelihood is sort of defined up to a constant multiple sort of, and also like, because I care about the maximum, it doesn't matter if I normalize it. So I get log p theta 1 of xi, and you can see that the MLE basically finds the maximum of this, right? Argmax theta in parameter space. And so if I put an argmax here, you see that we have our MLE, right? And so you can identify this as this m theta of xi. So in this case, this m theta of x, this family is defined by the log of p theta, like the log likelihood of a single sample, in a sense. Okay, the like MLEs in instance of this, but the blueprint is fairly general. So is this clear, everyone? The blueprint is general, so I could, for example, take the m theta to be negative x minus theta squared. Okay, mn that I'm defining is this guy. So I'm calling this guy mn, capital M n theta. So mn theta is really that empirical average, m theta of xi. And if I do that, then this guy is going to be the function that I'm going to try to maximize, and the maximizer of this is the sample mean. The maximizer is the minimizer of the negative of this, and it's easy to see that the theta that maximizes sample. So sample mean is actually an estimate for a particular choice. If I take the m theta to be the negative absolute value for the deviation, the criteria, the objective function would be that, and the solution would be a median, which might not be unique, but a median of the sample median would be a solution. So the sample median, you can think of it as an M-estimate. Okay, so sample mean is 1, maximum likelihood, as you can see here, is 1. Sample median is 1, so it's fairly general. These two cases, in the special cases, are examples of MLE, but so for example, if the density has this particular form, you can see that if you do the MLE, you would get these two cases for a certain power P, but these are reasonable choices when if the density does not look like that, family does not look like that. Okay, so this gives you a prescription or a procedure to obtain interesting estimator. So you can think of this as a loss function. So in like machine learning or statistical learning theory, so you'd minimize the loss. So this is like the negative of the loss. Okay. And then there's the corresponding notion of z-estimators. So these are M-estimators because they maximize or minimize the criteria. There are z-estimators that find the solutions of certain like averages like this. So if you instead have like a sequence of size, this could be like, I can write it as psi theta. And instead of trying to maximize, I try to find zeros of this. The estimators that are solutions of these kind of equations are called z-estimators, or the approach is called like estimating equations or something like that. This is very close to the M estimation, because if you do unconstrained optimization on differentiable objective functions, so if there are no constraints, if I try to maximize this, the maximizers have to satisfy first order optimality conditions. So you take the gradient or the derivative, set it equal to 0, so you get a bunch of equations where these guys are now like the gradients of these guys. So the optimizers are among the solutions of this. So there's this close connection between Z estimators and M-estimators. So some people study these. Some people study these and some people study both. I'm going to focus on the M-estimation procedure because it's sort of easier to analyze and slightly more general, I would say. But there's this connection, okay? So far, so good. M-estimation, Z-estimation. These are some general procedures to get estimated, yes.
Should psi theta be like something product of psi theta or just a general function?
No, a general function, yes.
But presumably, like you could take it to be the inner function too. Or would that not be interesting?
Most likely not interesting because then you would end up with so you have to justify why you would take that. You can take it and then try to solve it, see what you get. The thing is this is going to be usually the size is going to be so because you're going to solve these system equations. If theta is d-dimensional, you need d equations. So size are usually multivariate. So there's sort of gradients of you think of the gradients of these. So if t like theta is like three-dimensional, the gradient of this would be three-dimensional. So the psi would be mapping x's to three-dimensional vectors. And so a good choice would be, for example, if this is the likelihood, what would be this guy? What a good choice for that. Yes, which has a name.
Score function.
The score function, yeah. So the derivative of this as a function of theta is the score function. So you put the score function here, that gives you a good choice. The inner product might work, but you have to have multiple inner products with like different measurements of xi's. A single one might not work unless theta is unique values. It's a different story. Okay, M-estimation, Z-estimation. Okay, sort of. So these guys, the thing that I wanna like skip is that these guys are usually like a good source of like method of moments approaches. So if you think of this as an empirical moment, so this is like approximating. So imagine 1 over n summation I from 1 to n psi data of xi. This is approximately expectation under the true parameter of psi theta of x1. Right. So what you're doing essentially is setting some of these empirical moments, like empirical moments based on psi, to 0 and then solving for theta. That's usually called the method of moments. And so this gives you generalized method of moments estimators.
Why exactly 0?
That's a good question. So let's say if this is C, would that work? I can move the C into the psi, right? Right. So okay, so because it came up, so you would do something like this. So these are the moments, like the psi, you take x to the k, for example, and then the actual moment. And then when you set it equal to 0, effectively you're equating the population moments to the empirical moments. You have to do multiple of these, not just one. But there is like a closed form solution for the k moment. So that would be a function of theta and then x to the k. Once I plug this into this, into the equation. So if you set the empirical moments of this equal to 0, This would be some sort of like mu k theta, if you want. Then you would get mu k theta equal to its empirical value. And then you have a bunch of these, then you solve. Right? Sounds good. I'll let you like think about this yourself. It's not something, but there is really, yeah. So let me just remove this. It's maybe confusing. This is not like the, yeah. So there is something inside there. Right? So these would give you method of moments or generalized method of moments. So like think about this slide and the next. So the next slide says that in the exponential family, let's say a certain method of moment approach is the same as the MLE. We already know this sort of, so we're going to skip this and move on to the actual asymptotics. Okay, so the main idea was to introduce this general framework and then study the performance as the n goes to infinity. Okay, so why would we want to do that? Because as you've seen, decision theory is pretty tricky for a finite sample size. So comparing estimators is difficult. There's the UMVU business stuff, but high-dimensional settings like more than one parameter, and also like even like realistic approaches, usually it's hard to actually calculate the risk and compare the estimators and come up with like optimal estimators for a particular finite sample. So you let n go to infinity and use IID settings. And then things simplify. Asymptotically, the picture becomes much more easy to like see. So you can compare estimators asymptotically. The particular property of an estimator. So in this asymptotic setting, you can ask for certain like desirable properties. So what are some of the desirable properties of estimators? A particular one is that if I draw IID samples from p theta naught, theta naught is a true parameter, and then I form this M-estimation, or sorry, the M-estimator. We'll say that this is consistent if this converges in probability to theta naught. Okay, so this definition is general. So this is just any estimator which is a function of these x1 up to xn. It doesn't have to be the M-estimator, but that's the notion of consistency. So if there is a true parameter generating my data, and if my sample size gets bigger, then the estimator converges to the true parameter. Okay, that's sort of the basic property that you can require. It's like sort of like unbiasedness asymptotically. Asymptotically, you recover the true parameter. You're not going to converge to something else. Okay, so this requires this notion of convergence and probability because this is a random quantity. So you have to specify what we mean by convergence. Okay. So how many people know what convergence and probability? Okay, quite. So any one of you guys wants to enlighten us?
Like the probability of using above like the estimate or you estimate something that also zero. The chance of it being above the number that the error being above that one is equal to zero.
Great. So you have the true parameter here. If I'm converging probability, I can find an interval, let's say, of size sort of epsilon above and epsilon below. So this interval. And then I calculate the probability that theta hat belongs to this, and this probability goes to zero. Okay, so the probability that theta hat n, let's say minus theta naught in absolute value. So this probability goes to 1. The complement goes to 0. So the chance that I'm outside here, so this probability, this is the probability that this is bigger than epsilon. This has to go to 0 as n goes to infinity. Okay, so like if you want to be like precise for every epsilon bigger than 0, you fix epsilon bigger than 0, you look at this event, the probability of it is going to go to 0 as n goes to infinity. Sounds good, yeah.
The sequence is in terms of the samples, right? So increasing samples. So
Yes, yes, yeah. Yeah, so you're assuming that theta hat, that n is like the sample size. So this is like the sweet spot. So there are stronger notions of convergence in like almost short convergence, but that oftentimes you see the statisticians work with this because this has nice frequentist interpretation. So on average, if you think of the probability as like an average, frequentist perspective, if you repeat the experiment many times and you form these so it seems that it says that for every epsilon there exists like some such a kind of large and such that this is less than delta. So this gives you some sort of a confidence interval. Okay, so with probability. So if you're a statistician, you would interpret this as this: for every epsilon bigger than 0, there exists some sort of n depending on epsilon, such that if my sample size is bigger than this, then with probability bigger than or equal to 1 minus delta, theta hat n minus theta naught is going to be less than or equal to epsilon. Okay, so this is just complementing this. Okay, so let me do this. Such that probability of theta hat n minus theta naught bigger than epsilon is less than or equal to delta. So that is the meaning of epsilon delta, meaning of the epsilon is part of it, and it has to be big enough such that this is less than, that's the meaning of this going to 0. This is a deterministic statement, and this is equivalent to if you complement it with probability bigger than 1 minus delta, theta hat n minus theta naught is less than or equal to epsilon. Okay, which in turn is equivalent to with probability bigger than 1 minus delta, theta hat n is in this interval. So if you're a statistician, you're very happy with this. This is some sort of a confidence bound. How do you interpret confidence bound? So in the frequentist sense, if you repeat the experiment many times, at least 1 minus delta fraction of the case, at least 1 minus delta fraction of the cases, theta hat n will be contained in this interval. It gives you how much samples you need to achieve that certain level. Okay, so for this reason, statisticians really like convergence probability. Sounds good? Okay, so and this what it's saying is that sort of whatever level of confidence you want, and whatever level of accuracy you want, there is a certain level of confidence. This should be going to be precise. For every epsilon and for every delta bigger than 0. So basically for every level of accuracy and every level of confidence, there exists sufficiently large n such that you can achieve that accuracy with that level of confidence. If you just expand this effect. So this is a very desirable property. This potentially depends on both, I guess. Epsilon and delta. And bigger than. Okay. And then you can generalize this idea. This is for a univariate parameter, but this interval is basically like in neighborhood. So the fact that this is less than or equal to epsilon is a neighborhood of theta naught in any space that you can define a neighborhood. So in a metric space, let's say I have a distance, I can define, this is like a ball of radius epsilon around theta naught. I can define a ball like this. So the distance of theta hat n minus theta naught being bigger than epsilon means that I'm outside that ball. So in Euclidean spaces, you put a ball of radius epsilon around this, and this is the event that this is outside this, and the complement is that it's inside. So it's a fairly general discussion. For example, you can take it to be the Euclidean norm, and then in the case of equal to 1, it would be just the absolute value. Okay, so most of the things that we talk about work in a general matrix space, but I often I either work with the Euclidean case or just the D equal 1 because of simplicity. Questions?
Are there non-Euclidean parameter spaces?
Sure, you can define whatever you want. Yeah, but I mean, some of the theory is sufficiently abstract, so there is no reason to restrict yourself to the Euclidean case. So we're not, for example, using the additivity, like, so some of the theory goes through, but whether it's useful or not, it's like up to you, how creative you want to be with your parameter. Okay, so there's a bit of notation here. So this is the notation that you're going to use for simplicity, little OP of 1. So Zn is little OP of 1 if Zn converges to 0 in probability. Okay, this is similar to little O of 1 in like real analysis or like non-probabilistic analysis. If you know what it means there, it just means O of 1 means the sequence that converges to 0. Here, it means we put a P here to mean that the sequence is converging to 0 in probability. So it's just a convenient way. You will see like this simplifies if you simplifies the arguments if you develop some sort of calculus of manipulating these old notations. There's a big OP of 1 that coming up like similar to big O of 1 in real analysis. Okay, so the basic source of the statements of convergent probability, if you remember probability course that you took, the basic source is the weak law of large numbers in probability. So weak law of large numbers tells you or gives you the basic blueprint of convergent probability. So what is the weak law of large numbers? Let's see how many people remember weak law of large numbers.
Sample mean can be used on the true sample mean, true means probability.
Great, yeah. So x1 up to xn, let's say, are drawn from some distribution. Then if I form the sample mean I from 1 to n, xi, this converges in probability to the mean of this distribution, which you can write as expectation of 1, if you want, in x, dp of x, whatever you want. But that's the sort of the basic convergent probability result. So sample mean. So like if you want to interpret this from a statistical perspective, so can I say like something is being consistent? This is saying that something is consistent for something else.
Sample means consistent estimator for the mean.
Yes, great. So the sample mean is a consistent estimator of the population. So whatever the distribution here it is, so this could be one member of like a giant family. It doesn't matter if the parameter that I'm trying to estimate is the mean of P. So sometimes you'd see like something, right? Like you can write it like that. Mu of P, this is really like a parameter of the distribution. So this thing is going to be my parameter. And so the sample mean is always going to be consistent with the mean. So there's some little assumptions here. So this distribution has to have a mean. So like this has to be finite. The modulo that this is the result of, let's say, the sample mean. Sample mean is a consistent estimator of the population mean. Okay. And then from this, you can get all sort of other consistency results. So that's like the building block. Questions? So let's just apply this to the M estimation that we had. So the M estimator that we had, so we had this sort of like empirical average, like a sample mean. And then we wanted to maximize this, if you remember, over theta. So assume that under the true parameter, if I take the expectation of this M theta applied to one of these samples, this is finite. So then I can apply the weak law of large numbers to conclude that this converges to the population mean. So population mean would be the mean of this, assuming that the distribution of x is coming from the true parameter. The expectation under theta naught of M theta of x1. And then, for example, I'm going to call this capital M theta. I'm going to call this little mn of theta. And so the weak law of large numbers is saying that this Mn, this is a random function. As a function of theta is a random function and it also depends on n. So this converges to m theta. But if you think a little bit about this statement, because it's a function, I have to specify what kind of convergence as a function is occurring. And the statement that we have for the weak law of large number gives you sort of pointwise convergence, okay, pointwise over theta. Pointwise means I fix one theta, for any fixed theta, this converges in probability to the same point method. Okay. It turns out that this kind of convergence is not enough to guarantee that the maximizers converge. Okay. I'll give you a very simple example. Even if probability is not involved, if you have a sequence of functions that converges pointwise to another function, there's no reason that the maximizers of this are going to converge to the maximizer. So you hope that if you maximize this population criteria over theta, you get theta naught. This is often sort of quite reasonable. So if your criteria is good, if this m theta is good, this has like a unique maximum at theta naught. And then this function is converging to that. So you would hope that the maximizer of this, which is your estimate, is going to converge to the maximizer of this, which is the truth, like theta naught. But that's not enough. What we'll see, like, guarantees this is this notion of uniform convergence. Uniform convergence means that, like, if you look at the deviation of the function mn theta from n theta, and you take the supremum over the entire parameter space, that the infinity norm over sup norm, this converges in probability to 0. So this, if this is true, if I can show that mn minus m infinity converges in probability to 0, if this holds, then good things happen. Then I can sort of like, sort of with a little bit of another condition, I can guarantee the convergence of maximizers. Okay. Just like a very tiny comment that there's like a weaker notion of convergence that guarantees convergence of maximizers. And it's like the optimization people really like it. We're not going to talk about it. They call it gamma convergence. Basically designed exactly to guarantee. It's weaker than uniform convergence, stronger than pointwise convergence. But just the name, you can Google it and like satisfy your curiosity what it is and what kind of conditions. But we're going to work with the uniform convergence. Sort of roughly the idea is, so yeah.
Why do we care about the maximum of that expectation? Is it because like I know like the sort of the estimators like R max over that thing. Is that like the same thing as what the expectations going to do?
So the thing is, this is converging to the, like I've formed that empirical average that's as n goes to infinity converges to that. So this object here is the candidate to the study because this is converging to it. And so I can study the maximizers of this, and oftentimes you design this correctly. If you design this correctly, the maximizer is just going to be exactly theta naught. Then you'd hope that if the maximizer is converging to the maximizers of that, and the maximizer of this is unique and is equal to theta naught, then you know it's just
It's a small point. You mean when you say the loss max, you mean the argument the maximum is and not like the maximum value, right? As in
yeah, maximizer. Sure. Yeah, this should be maximum. Thank you. Yeah, maximizer of m, or then the maximizer. Yeah, you can also talk about the maximum. We don't care about the maximum, but even the maxima doesn't necessarily converge. Neither the maximum nor the maximizer necessarily converge. So here's a very simple example we can go through quickly. So I have this like Muhammad sort of function. So you can write it mathematically, but there's this little peak here that's getting narrower as I increase n, and there's this peak that remains fixed. So as I increase n, so if you look at that mn, you can verify that this, like the height is 1, but the width shrinks. So if I pick any point, basically, it's 0, it's 0. And if I pick any point here before 1/2, this is going to shrink past that point. And so after a certain n, in the vicinity of that point, it just looks like 0. So it's pointwise converging to 0. So if you think about it, the pointwise limit of this is going to be like this function, 0 up to here, and then that. So that would be the pointwise limit. So there is, in the pointwise limit, there's no peak left. Like this peak is not there. But this peak is determining both the argmax and the maximizer of the converging sequence. So the maximum of Mn is 1, and the maximizer is, I guess, 1/n. So argmax of Mn is 1/n, maximum is 1. So this converges to 0. But the argmax of the limit is 1 always. Okay, so 0 does not equal 1, so the argmax doesn't converge. There's an example where the pointwise convergence holds, but uniform convergence fails. And you can argue that that's the case. Okay. So it gives you an example where you have pointwise convergence of this function through this, but the maximum of this is 1, maximum of this is 1/2, the maximum doesn't converge. Argmax is 1/n is converging to 0, and the argmax of this is 1/2, and clearly they don't converge. Like this doesn't converge to that. Okay, sounds good. Questions? So if we assume uniform convergence, I'll talk a little bit about what we need, but upgrading the pointwise convergence to uniform convergence requires some technical tools. But if you have that, so let's assume that we have this uniform convergence. And also I have this other criteria here, which we can say that M has well-separated maxima. Then this result is saying that if you look at the argmax of the sequence of functions, that would converge to theta naught. Okay, theta hat n is going to be consistent, so theta hat n converges to theta naught. And this one, it actually doesn't require you to assume that Mn is like that empirical average. So the fact that it's empirical average is going to come into when you try to establish this, but this result is very general. So if you have a sequence of random functions Mn theta that converges uniformly to M in probability, and this criteria, second criteria holds, which I'm going to talk about, then theta hat is going to be consistent for theta naught. So how do we? Okay, so let me maybe mention this. So this is stated slightly technically, but roughly what this is saying is that theta naught is the unique maximum of M, the limit function.
It should be saying like the true maximum is the global maximum is strict isolated maximum.
It is strictly, yeah. So this is sort of saying that even a little bit more than that. So if you have like theta naught, if you put a ball of radius epsilon around it, and then look at the value of the function outside this. So maybe this is like that. I'm putting a ball here. So the maximum outside this, basically, I should have like colored this. The maximum of the function, so this part. So you look at the maximum of this, that would be this part. Okay, so the maximum here is that. The true maximum is, the value of theta is like at this point. So this is saying that this value is higher than this value for any epsilon. Okay, so this guarantees that and theta is a unique maximizer. So isolated is sort of, yeah. So if, for example, you have something like, it's like if the maximum is flat, like this, once you shrink the epsilon, then it's not going to work. Okay, so that's the case. The case that this is like interestingly like avoids as well is like when this goes back up. So this is an example from the asymptotic statistics book that by Van der Waart. It's on the website. So this goes back up and asymptotically approaches this. It's not like the maximum or carries at infinity, another maximum. So this prevents that, because if that's the case, then in an interval outside, so outside in this green region, the supremum is going to be exactly m theta naught, and so this violates that. So it prevents the maximum or carrying asymptotically at infinity. So it's well separated unique maximum, sort of, right? For all intended purposes, you can think of it as just there is a unique maximum. Sounds good. So theta naught is the unique maximum, or like the well separated maximum, and we have uniform convergence. Statement is clear. Yes.
Is it like equivalent to like a strict concavity almost? Stronger.
Yeah, strict, for example, convexity would imply something like this, or concavity. Yes. So a strict concavity.
Globally, you don't even get close to, or you can get close, but you're certainly going to be less than.
Yeah, I think, for example, maybe that's a good exercise to do, that like a strict concavity probably imply this condition. Yeah, because asymptotically, like outside this, you're going to go down, and then near it, like there's no way, because of the strict concavity, that you'd have this flat part. So it prevents. Yeah, that's a good example. But this is sort of more general, so there's no assumption of like convexity. But I believe that that's exactly one special case. Any other comments, questions? So let me prove this. It's a little abstract, but the technique is very general. And this technique, if you understand it, sort of is applied everywhere. Even in high-dimensional statistics, more modern stuff basically rely on a variant of this argument. Some people call it the basic inequality argument. So it starts with a basic inequality, which is the proof. Is saying that if I look at the value of these random functions and at the true parameter, the theta naught, and if I look at the value at the maximizer, this basic inequality holds. So why does this inequality hold? The what?
It's a true maximum.
Theta naught is not a maximizer of it. But this is a maximizer. Right. So this is a maximizer. So if you rearrange, this is saying that basically that this is larger than this, right? Because this is the maximizer, this has to be, and there's no reason, I mean, this could be equal to that, but it's definitely less than or equal to the maximum, right? So it's saying that the maximum is achieved at theta height. So I have this, then I manipulate this, and I get interesting. So this is the basic inequality. So this is saying that, okay, so theta naught is feasible. We can say theta naught is in the feasible region. This is a maximum, so optimal. So the value of the function at the feasible point is less than or equal to the value at the maximum, or the optimal sort of solution. And then what I'm doing here is like adding and subtracting. Basically, I want the population copy of this, which is m, and then I also want the m of theta naught. So I'm looking at this difference in the population, and I'm adding and subtracting to the both sides of the equality. Okay, and then like with a flip over sign. So m theta naught minus m theta at n, that's the population version, and I'm just adding it to the both sides. You can see like with the signs. So this gets multiplied by that. So I get the same thing. So I'm just adding this to both sides. So if you stare at it a little bit, this is added to both sides, and this is basically like the flip of this, but evaluate the population quantities. Sounds good. Okay, now interesting things happen here. So here I'm comparing mn to m at this point theta hat n. And here I'm comparing mn to m at this point theta naught. And both of these, so this is like a little triangle inequality. This is less than or equal to the absolute value of mn theta hat n minus m theta hat n plus the deviation at theta naught. So this is triangle inequality. Right? And so this is mn minus m at one point, this is mn minus m at another point, both of which are bounded by, so this is bounded by mn minus m infinity. The other one is also bounded by mn minus m infinity. That's the supreme deviation. So this entire thing is going to be in the end bounded by this. Right? You're assuming that this is converging to zero and probably so. This gives us an interesting inequality. But that's sort of, is that clear so far? A comment before we move on. This one is converging to zero by the Weak law of large number because theta naught is fixed. So I don't need to bound this by that. So this is going to go to zero. The main thing that I'm controlling with uniform convergence is this. So this quantity is the difficult quantity because of this term, basically. So you're evaluating mn, which is a random function, at the maximizer of itself, which is a random function dependent on its like mn. So theta hat n depends on mn, both are random. So controlling this is very difficult. Unless you know something about the specific, but even if you know something about the specific, because of the dependence between theta hat and n, you can't condition it, for example, theta hat and so forth like that. So that's what uniform convergence is sort of trying to avoid or like circumvent. So how to analyze this basically do that. And you can see it might be like necessarily not the best option because it's controlling over the entire set, but this is a particular one that I care about. Maybe there are better ways, but in general, it's very difficult to find any better way to control that. Okay, so that's the inequality that we got. So what I ended up showing, because this is going to zero by assumption, what I'm saying is that this is converging to zero by assumption, okay? And sort of you can also see that this is bigger than or equal to zero. So why is that? This is bigger than or equal to zero.
The true function, sigma zero is the next.
Yes, great. Yeah, so that's the second condition, sort of, that theta naught is a maximizer of n. So theta hat n is, I'm computing at m at like a generic point, like a random point, but theta naught is the maximum. So this is going to be bigger than that. So it's bigger than zero, and this other side is going to zero. So we have like sandwich between zero and something that going to zero. So this deviation is going to zero. At this point, really, what you showed is, is this clear? So at this point, what we showed is that if you think of this as a distance, so I can define a distance in on the parameter space. Let's call this. It's like, what should we call this? I don't know. Rho. Theta and theta prime define it to be m. What I say, the distance at it's not the distance, but at the true parameter. So m theta naught minus m theta, you're saying it in this distance, theta hat is converging to zero. So it's like a distance anchored at this. It's going to be positive if you anchor it at this because this is going to be bigger than or equal to zero. It's not a distance, but in this metric, sort of like a metric, it's going to zero. That might be good enough for you. So we're sort of establishing like consistency in sort of like a pseudo, like not pseudo, but like a fake metric, because this is like a deterministic function. But what the next step is doing is trying to translate convergence in this awkward metric to a convergence in the distance that we like. Okay, and that's exactly where this condition is coming. And it translates like this distance to this distance, sort of. So let's see how that works. So if I define this quantity, eta epsilon to be deviation of m theta naught minus the maximum of it outside the ball of radius epsilon around theta naught. So that deviation is exactly like this part. So this minus the other side, this is strictly positive by assumption for every epsilon. So this is going to be strictly positive. And then I can pull this supremum out, right? And I get the second equality. So why is that true?
And they're not, then in the supreme way, it's actually put inside. Right?
Yes, and then when you move the negative sign past the supremum, you flip it to infinity. So I move it inside, I get, if you want to do it in two steps, you get negative m theta, and then you move m theta naught as well inside. So you get that. So this is saying that if you look at this deviation, that metric that we have, the smallest that it can get outside a ball of radius epsilon around theta or the center of theta is eta epsilon. That's what we define, and this is positive. So that's my definition. Now, what we have established is something about this quantity. Okay, so let's try to work with this thing that I mentioned here. So suppose I want to establish the probability that theta hat n minus theta naught in distance. The probability this is bigger than epsilon is going to 0. So this probability being bigger than 0 implies that this probability. Oh, sorry, we have this inequality. Let's see if people can argue this inequality. Why do I have this inequality?
The right hand side is good. Yeah, it's
Right.
It's kind of like triangle almost, isn't it?
No, it's not the triangle. So it's okay. So it follows from this statement. So why this statement is true? That's just like definition of this quantity, right? This is saying that if theta is bigger than epsilon, then this is bigger than or equal to that. But this is true because this is the infimum over all possible theta that satisfies this condition. So this is the smallest that any theta that's outside that ball can be. So this deviation can be for any theta that's outside that ball. So this implies that follows from the definition. And this logical implication can be translated into a probability statement, okay? That people know, right? So if an event implies another event, it means that this event, the event that this holds, okay, so this event, this holds for any theta applied to theta hat n. So this is an event now. So I have that this implies m theta naught minus m theta hat n bigger than or equal to eta epsilon. Because this holds for any theta, it should hold for, this conditional statement should hold for a random quantity. And this means the event that this happens is a subset or included in the event that the other one is happening. So this is like logical implication, if you translate it to the language of events, means inclusion. Okay. And if I have inclusion, then the probability, so if you have A included in B, then probability of A is less than or equal to probability of B. So this is saying that probability is monotone, basically. Because of this, if I apply probability to both sides, I get that equal. Okay. And this is bigger than that implies that 2n times mn minus n infinity is bigger than epsilon because of this inequality that we established. So this quantity is bounded by twice that. So if this side is bigger than something, then it implies that this is bigger than something. Again, another logical implication, which means inclusion. So this bigger than that implies that this is bigger than that. So this is another logical implication turned into inequality, and this goes to 0. the reason why this goes to 0 is because it's strictly positive. And so we know that this conversion probability for any sort of positive delta that I put here, because if it's positive, it's going to 0. So the only place that we use that second assumption is sort of that this is not going to be 0. It's going to be always positive for any epsilon. Any epsilon you take here, you get a positive quantity here, and this has to go to 0 as n reaches to infinity. So we established that the probability of this is going to 0 as n goes to infinity, and that's exactly what conversion probability means. Okay. So there are two steps, one like basic inequality, saying something about the convergence of this, and then translating this into a distance between theta hat and theta naught in the distance that you like. And this is sort of what this guy is doing. And if you like think about this proof for a long time, you'd see like this is a very general argument, and you can sort of apply it in different situations. Okay, very simple argument, but there are a couple of like key moments that you have to think about. Okay, so it gives you a general result, assuming that you can establish these two conditions. So any questions? Consistency of M-estimators. So that's our main result for today, consistency of M-estimators. Questions? Okay, and then there's like a little like exercise here that you can replace. So this doesn't have to be the exact maximizer, it could be an approximate maximizer. What you want is that if you go through the argument, you want the mn theta hat n be bigger than mn theta naught minus a little OP of 1. The term that goes with probability to 0. So this is saying that this is bigger than this, but not exactly bigger than this, but maybe you have a slack here that goes to 0. And if you go through the argument, everything goes through. Okay, so it works for approximate maximizers as well, which is interesting. Okay, a few comments about the conditions. So the conditions of uniform convergence, some sufficient conditions can be found in Keener, chapter 9. So for example, if the parameter space is compact, this function is continuous for every x, and sort of this sup norm, this is supreme over the parameter. This is the infinity norm of it. If you take the expectation is finite, then he has a result that shows that uniform convergence holds.
Is this like similar on zealous convergence?
Uh,
It's not different. But the thought is also to equivalent condition for uniform convergence when the numbers compact.
what does that say? Sorry.
So on zealous goal, it says that if you're compact metric space, then uniform convergence along subsequence is equivalent to uniform boundedness and echo convergence.
So uniform convergence along sequences. Like this is like compactness, right? I forgot. It's like analysts really like that theorem. So uniform convergence along subsequences. And then what?
Is it always uniformly bounded, like the bounded?
Oh, okay, that's okay. So this is a uniform convergence of a sequence of functions, right?
Yeah.
Along a subset. Sorry, yeah, okay, compact the space. Okay, uniform convergence of sequence of functions along a subsequence.
If it only is uniformly bounded and equivalent.
Uniformly bounded and equi-continuous. Yeah, so this is, yeah. So this is sort of like boundedness, but it's not exact boundedness. So it's like bounded in.
Is it more about saying that data sent to end not specify how continuous this is? What was also you can specify how continuous they are.
Yeah, so this just says continuous, just regular continuity, right? Like just for every x, it's yeah. The question is like the family. So okay, so you have to think of this as a family of. So the functions are okay, parameterized by theta. So you're looking at this family. Yeah, theta maps to m theta of x as x varies in.
Yeah. Yeah.
Um,
That is all just because we want uniform version of the like we drop that complement function. I use some degree that it's like every hospital. It gives you almost uniform convergence.
right. Okay. So continuity gives you like, okay, rough uniform convergence. Yeah. So this is sort of weaker in a sense, right? But like this, I might come back. So we're going to come back. There's a notion called the stochastic equicontinuity, and stochastic equicontinuity sort of guarantees it's like weaker than so you can guarantee this sort of convergence if this mn is converging, like if this mn theta, the family is stochastically equicontinuous and theta hat n converges. If it's like if it converges, then this thing converges. But yeah, so there is some connections, but these conditions seems to be like weaker than like these exact notions, right? It might be because of, as you pointed out, like the probability structure. But in any case, so even if this is not compact, you can just like state results like this. The reason why I'm not going to talk about this because this is like a huge topic. So these are called the results that give you these conditions are called uniform laws of large numbers. And another term that you can search is like called empirical process theory. And this could be the topic of like an entire course. Okay. So there are some high-powered tools that exist or people have developed to establish these kind of uniform convergence results by just operating uniform like law of large numbers to apply uniformly across a class of functions or a class of like parameters if you want. So rest assured that there are conditions. So you can read this theorem 9.2 is pretty readable, I guess. And it gives you proof. But we're not going to go over that. And then there's this condition B. Condition B is also going to be sort of sufficient conditions that omega is compact, m is continuous, and m has a unique maximizer. So if things are compact and if the space is compact and is continuous, sort of this is equivalent to unique existence of unique maximizer. So this is an example where the space is not compact. And so you could at infinity things happen. But if the space is like parameter space is compact and is continuous and you have a unique maximizer, then that's enough. So one more point here, uniform convergence. Yeah, actually I have the proof here. You can read it for yourself, the proof of the uniform convergence. Oh, sorry, not the uniform convergence, the second condition, why like this is enough. But uniform convergence generally requires the parameter space to be small in a sense, or like your function class, the class of functions that you're trying to work with is small. So the size of that parameter space is usually what matters. So compactness spaces are essentially like finite sets. So if the space is too big, then you're in trouble. So what I want to do is like to show you what that criteria looks like. So this was like, remember that's our M function. That's the limit. So we're saying, for example, in the M estimation procedure, Mn, which is So this was the Mn, which is 1 over n summation I from 1 to n m theta of xi. This converges in probability to this limit criteria. So let's see what for MLE, for example, what this looks like. Okay, so for the MLE, I have this is going to be the log likelihood, right? So this is going to be log likelihood, and if I want to study the maximizer of this over theta, I can equivalently look at this quantity. So this is just the same thing, but I'm subtracting. So log p theta of x1 minus log p theta naught of x1. Because this theta naught is fixed, and I'm maximizing over theta, that doesn't matter. So adding this here doesn't matter in the maximizer at theta. Of course, I can't put it in there and try to maximize it because this requires, like for in the sample, this requires me to know the true parameter. But to analyze the population level, I can just do it. It doesn't change the maximizer. So if I do that, so calculate the capital M theta for this little m theta, then you can see this can be written as an integral. So integral of negative log p theta naught. So I'm just flipping the numerator and the denominator. So I get a negative sign, and then integrating with respect to the density of, so x1 has the density this is the true density, right? So I'm evaluating this expectation under the true distribution. So you're assuming that x1 has this density. So that's there, and then this is just m theta. So this is, or rather, this is negative m theta of x. And these negative signs sort of cancel out. So this is called, hopefully a lot of people know this, this is called the KL divergence. Okay, so the KL divergence between these two densities, one here and the other one. So the PQ between two densities is integral P of x log P of x divided by Q of x. So it's like a distance. It's actually like a squared distance between density. So this measure is a measure of how close two densities are. And using a little bit of so the inequality, you can show that this is always non-negative. And it's going to be 0 only if P and Q are the same density. So it's a non-negative measure. So this is always true. So if they're different, this is going to be bigger than 0. If they're equal, it's going to be equal to 0. So it acts like a distance. It's not a proper distance. It's not symmetric. It doesn't satisfy triangle equality. In fact, it looks like squared distance, if you think about it. But in any case, so that's the population level criteria for the MLE. So it will have a maximum. So this, because the m theta would be for the MLE would be negative of this, right? It has a maximum at the true density. And for all other densities, it's going to be like strictly negative. So the true density is really the maximizer. And whether it's like satisfies that uniqueness condition, you need a little bit of more information. If these conditions hold, sort of, you don't need to do anything. So if the parameter space is compact, M is in general would be continuous, then and you have the unique maximizer criteria, so that would be satisfied. In general, you might be able to show like an inequality like this. So the KL divergence is going to be lower bounded by some gamma of the distance. I would say this is called, like, you could refer to this, it's not a common name, but strong identifiability criteria. So this is saying that if the density gets small, then it forces the distance of the parameters to get small. In particular, if this is 0, it has to force the parameters to be equal. So that would be identifiability. If it turns out that this is 0, but the distance is large, it means that there is some sort of an issue with identifiability. So you have parameters that are very different, but the distributions are very similar. So you want to prevent that. So you want your parameter, this, so if you have two parameters, so this is like the space of parameters, is the space of densities. You have parameter theta naught and then parameter theta. This maps to p theta naught. This maps to p theta. If these two get close, you want the parameters to get close. The closeness here, because statistics tells you how to estimate the densities. So you can estimate the density correctly. So if your density is close to the true density, you want the parameters to also be true in whatever distance you have. And if you have some sort of inequality like this, that forces. So this is like improve extending or making identifiability more quantitative. So how far I need to be, like if I have this far in the space of probabilities, how much I can bound the distance of the parameter. So if there's some function like that, then it would be the case. So for example, you can calculate this the k-level in exponential families, and generally speaking, it would lead to some sort of a Bragman divergence. So if you do it, for example, for the exponential family, you end up with that Bragman divergence. Not the exponential distribution, which is special case of the exponential family, you end up with this Bragman divergence, and this satisfies that sort of criteria that we had. But in general, so the punchline is that for the MLE, the condition sort of holds. Like you have the unique maximizer, there's just a tiny bit of information that you need to make it such that bad things don't happen at infinity. And if you don't have any infinity, then it's fine. Sounds good. So MLE is in general consistent because the K-level. So if someone asks you why the MLE is consistent, you first say it's not in general consistent. You have some example in your homework problems that it's not consistent. But when it's consistent, it's because sort of that the K divergence has a unique maximum or like a minimum at the parameter, the density of the parameter. Okay, sounds good. Okay, see you next time. Thank you.